In the last couple of modules, we have talked about how one can study how the bond breaks. So, we talked about what is called snapshots of bond breaking. Today, and also we have talked about an important excited state process, twisted intermolecular charge transfer. Today, we will discuss another process, solvation dynamics. And the reason why one is interested in solvation dynamics is this. Even in class 11 or so, everybody is familiar with this diagram, right. So, what this diagram tells us is, why is it that polar molecules are soluble in polar liquids? Sometimes you talk about why ions are soluble in polar liquids. So, the reason why polar molecule is soluble in polar liquid is that the energy is minimized due to favorable solute dipole solvent dipole interaction. This is something that everybody knows. Why is it that nonpolar solutes are not soluble in polar liquids? Yes, so generally we say they are hydrophobic, right. So, some people say that this term hydrophobic is not right, because it is not as if there is any repulsion between these nonpolar solutes and polar solvents. It is just that if you put it in terms of a little more general interactions, the cohesive force of the solvent in that case is much more than the adhesive force between the solute and solvent. It is just that the solute molecules like each other very much. So, they do not care about the solute molecule, that is why they do not dissolve, because after all the same nonpolar solvent solute does dissolve in nonpolar solvents. Okay. But we do not have to get into that for the moment. Here we are going to concern ourselves only with solution of polar solvents, polar solutes in polar solvents. Now, the question that one asks in solvation dynamics is, how much time does it take for solvation to take place? And the reason why this question is interesting fundamentally is that solvation of polar transition states are polar more often than not. We have seen an example of such a polar transition state in case of say DMABN in the last module. So, solvation of these steps is often the rate determining step. So, if you know solvation dynamics, in principle you should be able to tell how much time a reaction takes place. So, this would be a very important step, this is a very important step in understanding reactions that take place in solutions. So, there is a lot of literature, this one for example published in 1991, where it says that activation of transition state, this has been studied for reactant and solvent energy flow for a model SN2 reaction in water. This reaction is chloride reacting with CH3Cl forming Cl CH3 plus chloride. It might look trivial, actually it is not. How do you know that this chloride is going in, that chloride is going out? You can do it easily by using different isotopes of chlorine. And the good thing about this is that what kind of potential well would this reaction have? If I think of reactant energy of product, it would be a symmetric double well potential, right. So, it turns out that for this thing, this kind of reaction, the rate determining step is solvation. Another Jack's paper published in 1985 by another stalwart Kosovar. This was on mechanism of fast intramolecular electron transfer reaction. There he made a comment, solvent motion controls the rate of fast intramolecular electron transfer. And then if the solvation is slow, if it is too slow, then it may not be actually complete, before that the reaction might take place. If that is the case, then you can have barrier crossing not only in the forward direction, but also in the backward direction. So, how fast solvation is often determines the dynamics of reactions involving polar intermediates, polar transition states. So, before we get into the question of how much time it takes for solvation and how you determine it experimentally, let us remind ourselves of something that is very fundamental in this field, not dynamics really, but how do you get some quantitative measure of solvation experimentally. Well, of course, experiment here starts with some theoretical model, and the theoretical model one uses here is Onsager reaction field model. This is discussed in detail in Lakovich's Principle of Fluorescence textbook, and it provides reference to the original papers for those who are interested. To put it very qualitatively, the model is like this. In this model, the solvent is modeled as a dielectric continuum, a block with the same dielectric constant everywhere. All right. Now, to consider the solute in the solution, first of all, we know once again from maybe class 6, class 7 physical science, we know that one of the properties of matter is that two different things cannot occupy the same space. So, if you are going to put solute inside the same inside the solvent, you have to create space for it. So, what Onsager did was that first of all, to consider the solution, he considered a spherical cavity, the diameter of which is exactly the molecular diameter of the solute. So, you have this dielectric continuum, some dielectric constant epsilon, and you have a cavity in it. What is the meaning of cavity? Epsilon you can consider it to be 0, there is nothing in it. Cavity means vacuum, and the size of the cavity is that the molecule can just fit in that cavity. So, that is how solvent is modeled. The solute is modeled once again without considering the chemical structure. So, if you see, this is a physical model, right. If you look at other physical models, if you think of things like say bond charging is another process that takes place that is considered for solvation. In all these physical models, there is no molecular structure, because if you consider molecular structure, you have to use quantum mechanics. So, these are models that are actually formulated using classical mechanics, and it does almost all the work. So, in this case, the solute is modeled as a dipole moment, which fits exactly inside this cavity that we have created. Okay. So, see, if I take water and if I take some aprotic solvent which has the same dipole moment, they would be modeled in a similar fashion, right. Dipole moment of that same diameter, provided the diameter of the molecules are also same. So, what you would miss out on in this model is specific intermolecular interaction like hydrogen bonding, all right. So, that is something that this model cannot accommodate. So, this model would work only when the interaction is purely electrostatic. Okay. Now, when I say purely electrostatic, why am I saying that? I am saying that because all the interaction that arises henceforth is because of the presence of this dipole moment inside the cavity. Until now, what have we said? Epsilon is same everywhere. Now, the moment you put this dipole moment inside the cavity, what will happen? Let us say the dipole moment is placed in such a way, you see this minus sign here, can you see? Yeah, minus sign inside the spherical cavity. Let us say that is the negative end of the dipole. This plus sign, let us say that is the positive end of the dipole. That is how the dipole is aligned, let us say. What will happen? This plus charge here is going to polarize the dielectric in its nearest vicinity, so that the dielectric now develops a minus sign here. The minus sign of the solute dipole on this side is going to polarize the dielectric around it, so that dielectric in immediate vicinity has a plus sign. So, what we generate even without considering molecular structure is micro heterogeneity in the solution, micro heterogeneity around the solute molecule, solute dipole, let us say, all right. So, now what is the situation? You have a solute dipole, and the solute dipole is contained in a cavity, one side of which is minus, one side is plus. So, one side minus, one side plus, what does that remind you of? One side minus, one side plus. What do you create that way? Capacitor, yes, you create an electric field, right, plus and minus, of course, a field will be created. Now, this field is created as a result or as a reaction to the introduction of the solute molecule in the cavity, is that right? So, this is called Onsager reaction field. I am skipping the entire mathematics here, I am trying to build the physical justification. Mathematics, you read Lakovich's book, you will understand, it is not very difficult, but Sometimes what happens is when we do just the math, we lose the, we do not even think of the physical insight, that is more important. So, what you have here is you have Onsager reaction field produced as a result of introduction of this solute dipole into the solvent, which is a structureless continuum. All right. Now, the dipole is subjected to this reaction field, right. So, what will happen? And the good thing is that the dipole is nicely aligned with the reaction field also, because the reaction field is produced as a result of the dipole. So, minus side of the reaction field is near the plus side of the dipole moment and dipole, and the plus side of the electric field is near the minus side of the solute dipole. So, what kind of interaction will you have? You will only have stabilization. Yeah? If you had a fixed field, let us say I have two plates and I apply an electric field there, one plate is positively charged, one plate is negatively charged. Inside that I forcibly turn the dipole around, then you can have repulsive interaction as well, not in this case. In this case, the interaction is intrinsically an attractive stabilizing interaction, because the field is produced as a result of the field is produced in reaction to the solute dipole, and so the solute dipole is nicely aligned to it. Okay. So, this field is going to stabilize the dipole, right. You are going to have stabilization as a result of interaction of this dipole with the reaction field. Okay. So, this is what the story is. Now, think of a situation where I have a molecule whose ground state is more or less nonpolar, excited state is polar. Can you think of any such molecule? Yeah, ground state is nonpolar, excited state is polar, dipolar. So, when charge transfer takes place, of course, one side of the molecule will become positively charged, one side will be negatively charged. So, DMABN could be an example, or nile rate could be an example, ANS, TNS, all these things could be examples. So, when that happens, according to Onsager reaction field, this would be the situation. Now, we bring in the structure of the solvent dipoles here. We are still not considering molecular structure, but we are at least recognizing the fact that these solvent molecules are dipolar in nature. So, in the ground state, the solvent dipoles are oriented in whatever way they are, because ground state dipole moment of the solute is, well, let us say less, not 0, maybe less. Here it is said it is, I think, mu g. Mu g is the dipole moment of the ground state. In the excited state, you have a different dipole moment mu e. In this case, let us say mu e is greater than mu g. Now, what will happen? You will have stabilization due to Onsager reaction field. If you go through the reaction, you will see that this picture is only to recognize the molecular nature. The derivation is completely based on dipole and field, no molecular structure at all. But since we know that solutes are dipole moments, we can think that these dipole moments will reorient, so that you have on the minus side of the solute dipole, you have solvent molecules pointing the plus sides, and on the other side you have the solvent molecules pointing the minus side, and that causes the stabilization. Okay. So, this is the molecular picture. Onsager reaction field is the gross physical derivation. So, then what happens to the corresponding ground state? Should we have, here in this diagram it shows that the ground state of this solvated species has a higher energy compared to the ground state of the unsolvated species. Why is that so? Ground state means the dipole moment is gone, dipole moment is back to mu g. So, why is it that this arrangement has a higher energy than this arrangement? Because, yes, you are right. In this case, it was this structure because it is not only solute solvent interaction. So, if you read say Bokris Reddy's book on electrochemistry part 1, you will see that while considering solution of a polar solute in polar solvent, you consider not only solute solvent interaction, but also solute solvent-solvent interaction, because let us not forget that solvent molecules are present in very large number. What is the concentration of water in water? 55 molar. So, there are millions of solvent molecules compared to like one solute molecule. So, solvent-solvent interaction also contributes very strongly to the energy of this solution. So, here the thing is, in the excited state you go from this unorganized solvent situation to organized solvent situation, or what is called the solvent-Berg situation, because of strongly favorable solute-solvent interaction. However, if the dipole moment is restored from the high value of mu e to the low value of mu g, then that favorable solute-solvent interaction is gone. And when that is gone, what is lacking in this structure is the favorable solvent-solvent interaction that is present here. So, this is actually more unstable than this. So, you can draw an energy cycle like this. So, what will happen if you look at absorption spectrum and emission spectrum? You record absorption spectrum and you record emission spectrum. If you go to a more polar solvent, then stabilization will be greater. So, the Stokes shift between absorption and emission is going to be larger, right. So, here Stokes shift provides a way of telling how polar the solvent is, and of course, it will work only when mu e is greater than mu g. So, this is some data using ANS, and you can see how emission spectra are getting redshifted, and if you go through this Onsager reaction field model derivation, you will arrive at something that is equally well known, that is called Lippard-Mataga equation. And Lippard-Mataga equation is something like this, where it says Hc delta nu means nu A minus nu F, where usually these are written in terms of wave number. The Stokes shift in wave number is equal to 2 delta F by A cube mu e minus mu g whole square plus some constant. What is mu e minus mu g? The difference in the dipole moment created upon excitation. The dipole, difference between the dipole moment created upon excitation and dipole moment of the ground state. What is delta F? Delta F is this. We had referred to delta F in one of the earlier modules, epsilon minus 1 by 2 epsilon plus 1 minus n square minus 1 by 2 n square plus 1. This is a measure of what is called orientation polarizability of the solvent. So, the idea is that if you make this plot of nu A minus nu F Stokes shift against delta F, then you are going to get a slope which is proportional to square of mu E minus mu G. So, greater the charge separation in the excited state, steeper will be the curve, right. And here we have an example of ANS versus TNS. You see that in this case delta mu turns out to be 9 dBi, in this case delta nu turns out to be 46 dBi. So, of course, this has a much more polar excited state compared to ground state. So, this will be a better marker of polarity compared to this one. Okay. So, what we have presented so far is the effect of solvation on steady state spectrum. We have not talked about dynamics yet. So, the question is, how do we study the dynamics of the excited state going from unsolvated one to a solvated one, right. That is what we want to discuss. Now, in this case, theory preceded experiment and lots of theoretical approaches, homogeneous dielectric model, inhomogeneous dielectric model, dynamic exchange model and molecular theories. You can see that in the order that they are written, you are actually going from a coarser theory to a finer theory. So, start with a model where the dielectric is homogeneous, as we have said already, Onsager model. Then you have to consider that dielectric may not be homogeneous, because after all, once again if you go back and read some basic physical chemistry textbook like Bockris and Reddy's electrochemistry book, what is said is that, see, in the immediate vicinity of an ionic solute, what is the dielectric constant of bulk water? 80 or something like that, right? What is the dielectric constant of water around, say, sodium ion? Yeah, much less. It is about 5. It is about 5, because the natural orientation of the water dipole molecules is disrupted in the immediate vicinity of sodium. There solute solvent interaction takes place. So, now just around the solute it is 5, in the bulk it is 80. So, it is impossible that there is a step jump from 5 to 80, right. So, it goes in steps. So, first solvation shell, second solvation shell, third solvation shell, that way you have a gradual change from 5 to 80. Well, when I say gradual, it is not really very gradual, it is quite steep, but inhomogeneity of dielectric is an important factor that has to be accounted for, and that has been done in theoretical approaches. Then when you consider the molecular, well, even before that, the third thing that you have to consider, and we are going to harp upon this a little later as well, is dynamic exchange. See, this is not a static picture. You have a solvent Berg model, fine. You have some of the solvent dipoles oriented nicely around the solute dipole, but it is not as if that the solvent dipole that is there present in the first solvation shell is going to be there forever. It is not as if the solvent dipoles that are not bound by the solute are going to be there forever. There is an exchange between the two, and as it turns out that this exchange between bound and free dipole solvent dipoles actually has an important role to play in the dynamics. Because when you talk about dynamics, what do you have to do? You have to write a lot of differential equations, right. What do we do in kinetics? First order process, second order process. What happens when we talk about some complex process? If there are several steps, you have to write differential equation for each and every step, right. Here, since dynamic exchange is a reality, one needs to account for it while building the model. And finally, you have to consider the solvent molecules as solvent molecules, not just dipoles. The problem with that is that how many solvent molecules do you have? Avogadro number, let us say. Yeah. If you are going to consider all of them to have some particular structure and you are going to use quantum mechanics for all of them, that is not going to work, right. So, very often what is used mostly here is statistical mechanical models, statistical mechanical models with explicit solvent structure. Okay. So, this is how the theory has evolved, and you can get an overview of this different kinds of theories from this very informative review by Professor Biman Bagchi and now Professor Biman Jana. Solvation Dynamics in Dipolar Liquids, published in 2010. There are many other reviews as well. Now, one thing that has been referred to constantly while talking about solvation, dynamics or otherwise, is dielectric relaxation. Dielectric relaxation measurements are actually important here, because the longitudinal relaxation time in simple liquids, the solvation time. So, lot of dielectric relaxation experiments have also been done in this context, but that again gives a bulk picture. Dielectric relaxation measurement does not have the capability of going near a solute and looking at it. For that, one has to use spectroscopy. So, this module was an introduction to the process of solvation itself. In the next module, we are going to discuss how one can use ultrafast spectroscopy to study the dynamics of solvation.